Today we're going to talk about the fundamental theorem of calculus. And this theorem is basically what allows us to evaluate integral that has upper and lower bounds. We're going to talk about how to do that with a calculator. We're going to talk about how to do that by hand. But before we can talk about the how, we need to talk about the why the fundamental theorem of calculus works. And basically do a quick derivation of where it comes from. So in the graph below, we're given a function y equals f of t, and it's continuous on the interval from a to b. We're going to talk about a portion of that curve, not from a to b, but from a to some upper limit x, some x value, where we're going to stop, and we're going to call that area under the curve capital F of x. So I know this notation is going to get a little bit confusing because we're going to talk about capital F of x, but we're also going to talk about lowercase f of t, so you may need to pause and rewind or just give yourself some time to process through all these different letters. So the area under the curve, and the curve is f of t, the area under that curve just from a to x, we're going to call capital F of x. So we could actually write that out, the area under the curve from a to x of the curve, which is f of t, which means we need to differentiate we need to integrate with respect to t. We're going to call that area capital F of x. So let's talk about capital F of x. If we wanted to look at the derivative of that, so by definition of derivative, if I took the derivative of f prime of x, that would be the limit as delta x, or sometimes we call h, but we're going to call delta x because we're really looking at the x-axis here. The limit as the change of x goes to 0 of delta capital F over delta x. So we're just applying the definition of derivative to capital F of x. But now let's put that back into words. F prime of x, well, that's the rate of change in the area. So delta F, and I'm going to just write it as delta F instead of F prime of x. Delta F is the change in the area, and that's going to be equal to the width times the height, if we think about this in terms of rectangles. And the width is going to be delta x, so that's our width. And the height is going to be the value of the function. So if I'm thinking about this as in I'm breaking this into a rectangle at some particular value, the height of that rectangle would be the value of f of t at that particular x value that we're looking at. So I'm going to use blue for that. So the height at this value is going to be lowercase f of x because we're using that f of t function, but we're evaluating it at the value when t equals x. So this is our height. So we're saying definition of derivative gives us that f prime, capital F prime of x, is the limit as x approaches 0 of delta f over x, over delta x. So let's solve that equation with all the pretty colors. Let's solve that for f of x. So that means that if we so I'm going to just take this over here. If we solve for f of x would be equal to delta f over delta x, because I would just divide both sides by delta x in order to isolate f of x, little f of x. So why are we doing all this? Let's go back to what we originally started with, the integral from a to x of f of t dt equals f of x. So that would mean, so I'm going to rewrite that just so that we're looking at the same thing again. Now what happens if I take the derivative of both sides with respect to x? So that would give me that capital F prime of x equals d dx times the integral from a to x of f of t dt. And that's going to be equal to f of x plus some constant. But let's kind of look at what's happening with that constant. Let's let x equal a and find the integral from a to a of f of t dt. Well, that's going to be capital F of a plus some constant. Now let's think about this. We're taking the area from a to a. That area is going to be 0. Because we're not moving anywhere. We're not moving left, we're not moving right. So that area is going to be 0. So that means that 0 equals f of a plus c, which means that c is going to equal negative f of a, capital F. So going back up to this original statement up top, the integral from a to x of f of t dt is going to be f of x plus c. But we now know what that c is. That c is negative f of a. So in reality, what we're saying, and I'm going to summarize the fundamental theorem of calculus in a little box because it is important enough, I should have saved more room for it. But in theory, what we're saying is that the area under this curve is f of the top minus f of the bottom, because otherwise we would be double counting a region here. So let's write that formally. FTC, the fundamental theorem of calculus, says the integral. You know what? I'm going to use a different color. I'm going to use purple, because purple is my favorite, and this is important. The integral from a to x of f of t dt equals capital F of x minus capital F of a. So what does that mean mathematically? That means that you are going to integrate to get capital F of x, meaning to get the antiderivative. Then you're going to evaluate the antiderivative at x, evaluate the antiderivative at a, so evaluate at the upper bound, evaluate at the lower bound, and subtract those two values. So for example 1 here, I'm going to have you grab your graphing calculator, so pause the video if you need to grab it. I'm going to show you how to integrate on your graphing calculator. So if you hit math and then hit 9 or scroll down to a button that looks like FN int, I just hit math 9, then you actually have the ability to plug in values on the bound. So you're going to plug in for number 1, -5 on the lower bound, +5 on the upper bound. If you hit the math function and you go over 1 tab, you should find absolute value. So hit that button and then type x cubed minus 6x, and then go over and fill in the x for the dx portion. So this is all on your calculator. By the end of this lesson, you will actually know how to do this particular absolute value integral by hand. But on your calculator, when you plug that in, you should get 198.5. For number 2, let's do this one by hand and then use our calculator to check. So first, we're going to integrate as if there were no bounds. So the integral of sine, the thing that I differentiated and got to sine from, is negative cosine of x. Instead of writing plus c like we did in the last lesson, we're actually going to evaluate this. So I'm just going to draw a straight line from 0 to 1. We're going to evaluate negative cosine of x from 0 to 1. There's no plus c because we are given information. We are given bounds on the integral. We only include the plus c when we have an indefinite integral, which means there are no bounds on it. So this is saying negative cosine of 1 minus negative cosine of 0. Well, negative cosine of 1 is just a number. This is going to become plus 1, so negative cosine of 1 plus 1. If you plug that in on a calculator, you're going to get 0.459. Now I want you to check. On your graphing calculator, hit math 9, type in the lower bound 0 and the upper bound 1, type sine of x, scroll over, dx, enter, and you should get the same value. Let's look at a couple more examples. Number 3 says set up a definite integral which could be used to find the area of the region bounded by the graph that's given, and the equation is given. The x-axis and the lines, x equals 0 and x equals 2. Well, these right here are telling me the bounds of my integral. So I'm going to integrate from 0 to 2. I'm integrating this function, so 2x squared minus 3x plus 2 with respect to x. There's the setup. And just for practice, let's go ahead and actually evaluate this integral by hand. And then if you would like, you could check this integral to practice your calculator skills using your graphing calculator. So the very first thing I'm going to do is I'm going to just apply the power rule and pretend the bounds are not there. So 2x squared is going to become 2/3 x to the third minus 3x is going to become 3/2 x squared. 2 is going to become 2x. I'm evaluating this whole thing from 0 to 2. You can put parentheses around that, but you don't have to. The nice thing is if I plug in 0, all of those terms are 0. So if I plug in 2, 2/3 times 2 to the third minus 3 over 2 times 2 squared plus 2 times 2. That's going to simplify to end up being 10 over 3. So we could find the area of that curve. Or under that curve, I'm sorry. It's going to be 10 over 3. So integrate the way that we've integrated before and then apply the bounds at the end. Number 4 is missing some directions here. It should say, given the graph to the right, answer the questions below. So I'm going to add that. That's better. So find the area under the curve from 0 to 5. So the area under the curve from 0 to 5, just going to turn this into a rectangle. We're just going to find the area of a rectangle. So that looks like 5 by 3, or 3 by 5 is going to be my area, which is going to be 15. Part B says write an equation for f prime of x on the interval from 0 to 5. So if I was I'm looking at this right here. If I was going to write the equation of that function, that is a horizontal line, which is a y equals 3 line, but let's write that as f prime of x equals 3. Part C, find the original function or find the antiderivative f of x if f of 1 equals 4. So first, let's take the integral of f prime of x. That's going to give us 3x plus c. So f of x equals 3x plus c. Then we're going to plug in the initial condition they gave us. 4 equals 3 times 1 plus c. So c is going to be 1. So f of x equals 3x plus 1. And then part D, find f of 5 minus f of 0. That's going to be 16. So if I'm plugging into here. F of 5 is 3 times 5, which is 15, plus 1 is 16. F of 0 is 1, and we're going to get the same area. So in part D, we're getting the same value as we did in part A. All right, let's move on. So here, we're paying due respect to the fundamental theorem of calculus. The fundamental theorem of calculus, again, says the integral from a to b, or from a to x, of f prime of x dx is equal to f of b minus f of a. So find the antiderivative, evaluate it at the top bound, and then evaluate it at the bottom bound, and you're going to end up with that value. Sometimes we're going to use what's called the start plus accumulation method, which means maybe you're actually given what f of a is or what f of b is. And that means you could, in theory, based on that information, manipulate this equation. Like here, I could actually add f of a to both sides, and that would get me here that f of b is equal to f of a plus the integral from a to b of f prime of x dx. So this is not anything new. It's just saying if you're given different information and you're being asked to solve, maybe you want to find what f of b is, then you may be manipulating the fundamental theorem of calculus to rewrite it in a way that's more helpful to you. Let's look at an example where that's the case. So if f prime of x is 3x squared plus 3 and f of 0 is 4, find the value of f of 2 without using a calculator. So we have f of 0 and f of 2. So if I was just to set this up normally, we're saying the integral from 0 to 2 of 3x squared plus 3 dx, well, that is equal to f of 2 minus f of 0. Since we are given f of 0, what we can do is move that to the other side. So f of 0 is just 4 based on this piece of information. So 4 plus the integral from 0 to 2 of 3x squared plus 3 dx equals f of 2. So f of 2, if I integrate 3x squared plus 3, I'm going to end up with x to the third. Well, I guess I can put 4 in front still. 4 plus x to the third plus 3x, and we're evaluating x to the third plus 3x from 0 to 2. Now, if we plug in 0, obviously that's all going to go away, so we're going to end up with f of 2 is 4 plus 2 to the third is 8. 3 times 2 is 6. So f of 2 is going to be equal to 18. So this start plus accumulation method is really dependent on the information that's given. So if you just took a quick look down at 5 through 9, on 5 through 8, you're going to just use the regular fundamental theorem of calculus, but on number 9, based on the given information, you're going to manipulate it a little bit to solve for the specific information you need, and that's basically using the start plus accumulation method. So go ahead and pause this video, work through 5 through 9, see how you do, and then go ahead and unpause the video and check your answers. So on 5, when we integrate, we're going to get 3x plus x squared, and that's being evaluated from 2 to 5. That's going to give us 3 times 5 plus 5 squared, minus 3 times 2 plus 2 squared. And when you simplify that, you're going to get 30. On number 6, when you integrate sine of x, you get negative cosine of x, and we're going to evaluate that from negative pi over 3 to pi over 3. So negative cosine of pi over 3 minus negative cosine of negative pi over 3. And when you simplify that, that's going to give you 0. On number 7, when you integrate that, you're going to get x to the third over 3 plus x, and you're evaluating that from 1 to 3. So that's going to give you 3 to the third over 3 plus 3 minus 1/3 plus 1. And when you simplify that, you're going to get 32 over 3. On number 8, I recommend that you expand that out to have a trinomial, because then it will be easier to integrate using the power rule. So when you integrate, that's going to give you 16x to the third minus 12x squared plus 9x, evaluated from 1 to 0. If I plug in 0, everything is 0. If I plug in 1, I'm just going to get 16 over 3 minus 12 plus 9, which is just going to be 7 over 3. Okay, number 9 is where you can use the start plus accumulation method. So the integral from 5 to 8 of the function with respect to x is going to equal f of 8 minus f of 5. Well, we know that f of 5 is 7, so I'm really going to say 7 plus, and then I can integrate this. This is going to become x to the third plus x squared minus 2x, and I'm going to evaluate this from 5 to 8. And when I simplify this all the way out, I'm going to end up getting 427. So there's some good practice integrating with bounds by the fundamental theorem of calculus and also using the start plus accumulation method. Now let's look at some more specific cases involving absolute value and total distance. So just like with derivatives, when we think about absolute value, you can really think about it as a piecewise function that splits at the vertex, because the vertex is where we would have differentiability issues. So really, absolute value of x you could think about as a function negative x for x less than or equal to 0, and positive x if x is greater than 0, right? It's the opposite of what you would have inside. If it's negative, it's what you would have inside if it's positive. Based on that, what you can actually do if you're integrating with absolute value is you can break it into two pieces that depend on which part of the step function we're using, because we don't want to integrate when we're crossing the x-axis. So thinking about this integral, which you could 100% plug in on your calculator and get the answer to, and I would say you should do that after we do it by hand so that you can check. But this would be the integral from negative 2 to 0, because on just regular old absolute value of x, 0 is my vertex. When I'm below the x-axis, my function is negative x dx plus, starting at 0 and going up to 3, the upper bound, our function is x dx. Now, if we evaluated this, here we would get negative x squared over 2, evaluated from negative 2 to 0, plus x squared over 2, evaluated from 0 to 3. And when you do those and combine them, you end up getting 13 over 2. And you should pause the video and type that into your calculator and see if you get the same thing. And because we can find the definite integral using absolute value, we can apply this back to something that involved absolute value, and that was speed. So since we know that the integral of velocity is going to be s of b minus s of a, if we're integrating from a to b, that gives us the displacements. If I wanted the total distance, and the total distance is the absolute value of velocity, we could integrate it using the same way that we did in this example here. So now we have ways to work around displacement versus total distance when we're looking at an integral. So let's look at, apparently these are misnumbered. Let's look at examples 10 and let's fix this here, 11. So number 10, let's go ahead and split this integral. This is going to have the vertex when x is equal to 1. That's going to be my issue. So I'm going to break my integral at 1. So I'm going to say the integral from 0 to 1 of the opposite of what's there, negative x squared plus 1 dx, plus the integral from 1 to 3 of x squared minus 1 dx. When I integrate that, that's going to give me negative x to the third over 3 plus x evaluated from 0 to 1 plus x to the third over 3 minus x evaluated from 1 to 3. The nice thing here is if I plug in 0, I'm going to end up with just negative 1/3 plus 1, which is 2/3. Plus, if I plug in 3 here, I'm going to get 27 divided by 3, 9. Minus 3 is 6. And if I plug in 1, I'm going to get 1/3 minus 1, negative 2/3. And then if I combined this all into just one fractional answer, that's going to give me 22 over 3. All right, number 11, find the total displacement traveled from time t equals 0 to t equals 3 of a particle whose velocity is defined there. This is a calculator problem. So number 10 says, this has the little calculator symbol that I give you, but number 10, we didn't actually need one, and you could use a calculator to check. On number 11, we have not talked about how to integrate or differentiate with natural log at all, so this is one you will definitely need your calculator for. So let's set up the integral. This is going to be the integral from 0 to 3 of our velocity function with respect to t in this case, since the function is in terms of t. So go ahead and plug that into your calculator. You're going to get 4.995. Notice this says displacement. It doesn't say distance. If this exact same question, that probably would be good to add to my notes, said distance, what you would do is on your calculator, you would take the absolute value of this function and then find that integral. The last thing we're going to talk about in this video is the second fundamental theorem of calculus. And the second fundamental theorem of calculus is really just the converse of the first fundamental theorem of calculus. The first fundamental theorem of calculus says if we start with the integral, we work backwards and use the derivative. Here we're starting with the derivative and we're working backwards and finding the function. You can also see down here it has this VU notation, and that's what's happening when the bounds are actually the value of a function. So something I want to point out is if you have a variable or a function in your bounds of your integral, you will evaluate the function at that particular value, and you will multiply that by the derivative of that as well. So I think that's going to make the most sense when we actually start working through examples. So let's look at number 8. The directions say practice the second fundamental theorem of calculus to find the derivative of the following integrals with respect to x. So we're finding the derivative. That's what the directions say. We're finding the derivative of the integral. So we are going to take this integral, we are going to differentiate with respect to x. When we do this, what we're really going to have is the function that's inside evaluated at x times the derivative of the upper bound. The derivative of the upper bound, the derivative of x, so let's actually write that, d dx of x. We're going to subtract the function evaluated at 0 times the derivative of 0. So let's look at this a little bit more. This whole piece is going to be 0 because the derivative of 0 is 0. So let's look at what's happening here. If I plug x into this inside function, that would give me 3x squared minus 5. That's what I get if I plug x into the function inside the integral, right? Because I'm taking the derivative of the integral, so I just have the function that's inside. These are inverse operations. I'm going to multiply that by the derivative of the upper bound. The derivative of the upper bound is just 1. So this is going to give me 3x squared minus 5. Let's look at number 9. Number 9 is a little bit more complicated because there's a variable both in the lower and the upper bound. So I'm going to evaluate the inside function, 3t, when t is x squared. So that's going to give, so actually I should say I'm taking the derivative with respect to x of this. So that's going to give me 3x squared times the derivative of that upper bound. The derivative of that upper bound is 2x. Minus, what do I get when I plug in the lower bound? I get 3x times the derivative of that lower bound, which is just 1. So this is going to give me 6x to the third minus 3x. Number 10. Number 10, I think you're going to like because you're going to see it on a much more conceptual level. I'm evaluating at g of x and f of x. So if I plug g of x in for t in this top function, so I'm taking the derivative with respect to x, that's going to give me g of x plus 1. I'm going to multiply that by the derivative of that upper bound, which is g prime of x, minus f of x plus 1 times the derivative of the inside, which is f prime of x, or the derivative of that lower bound, which is f prime of x. And that's really as far as we can go on that problem. I know these notes are getting long and they are almost done. I promise we're going to talk about average value of a function and then do one more example. So the average value of a function can be calculated just like you calculate what you think of as the average, the mean. So the average value of a function, given that the function is continuous on the interval that we're talking about, is going to equal 1 over b minus a, so we're looking at the endpoints there, times the integral from a to b of f of x dx. That is how you find the average value of the area, the average value. So this should sound, talking about average, should kind of sound like something we've talked about before, and that is the mean value theorem. So there is actually a mean value theorem for integrals. And what it says is, if this function is continuous, then at some point the function's value actually has to be the average value of the function. So if you are using MVT for integrals, remember that you always have to state the conditions before you use it. If you are simply being asked to find the average value, you are using this formula or equation up here. The average is 1 over b minus a times the integral from a to b of f of x dx. Let's look at our last example. Find the average value of f of x equals x to the third minus x on the interval from 0 to 2. So let's start there. Go ahead and pause the video and set that integral up. So we can perform that integration, x to the fourth over 4 minus x squared over 2, evaluated from 0 to 2, and then in front of that we're going to have 1/2. If we plug in 0, all of that is going to go away. If we plug in 2, we're going to get 2 to the fourth over 4 minus 2 squared over 2 times 1/2. That whole thing is going to be equal to 1. 1/2 times 2, which is going to be 1. Since f is continuous and differentiable, MVT for integrals applies, which means there does exist a c value such that f of c equals the average. So what we're going to do is say that the average, which is 1, is going to equal the function at some point, x cubed minus x. And for time's sake, you can plug this in on your calculator to solve, and you're going to get that x, which is the c value we're looking for, is 1.325. So key things in this lesson: the fundamental theorem of calculus says that we can integrate and then evaluate that function at the value of b and subtract that function evaluated at the value of a. We talked about how to integrate using your graphing calculator. We talked about the accumulation, the start plus accumulation version of this. We talked about integrating with absolute value and how that ties to speed and velocity. And we wrapped up with the second fundamental theorem of calculus and the average value of a function. Looking forward to spending more time on this in class. Thanks for listening.